Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on December 11th, 2025, about 5 days ago. It shows that for representation alignment in diffusion transformers, spatial structure in the encoder features, not global classification accuracy, is what really drives image generation quality, with spatial metrics reaching correlations above 0.85 with generation performance. The paper is titled, What Matters for Representation Alignment? Global information or spatial structure. And as we will see later, the implications for how we pick and tweak vision encoders for generative training are quite significant. Alright, Figure 1 makes the main claim very concrete. The left scatter plot shows that higher linear probing accuracy barely correlates with better generation quality, since the points are scattered and the correlation line is almost flat. The middle scatter instead uses a spatial structure metric and shows a strong downward trend, so richer spatial structure clearly predicts lower FID and better images. The right bar chart compares standard representation alignment with the new improved variant, where the red bars are consistently lower, meaning faster convergence and better FID across several vision encoders. Well, Figure 2 gives two concrete examples showing why spatial structure matters more than global accuracy. The overall layout contrasts a high-accuracy encoder with a spatially tuned one, using dog and lion query images on the sides. The heat maps in the central panels visualize spatial self-similarity, where brighter, sharper regions indicate stronger local structure around the red squares. The tables beside each set of maps report that, despite much higher validation accuracy, the global-focused encoders have lower spatial LDS scores and worse FID, while the spatial models win on both structure and generation quality. So, the previous figure gave intuition from a few encoders, and Figure 4 now scales this up across all 27. The left plot shows that linear probing accuracy barely tracks generation FID, since the points scatter widely and the correlation is only about -0.26. The four plots to the right, using different spatial structure metrics, all show tight downward bands with correlations around -0.85 to -0.9, so stronger spatial structure reliably predicts better image generation quality. Alright, the previous figure established that spatial metrics predict performance, and Figure 6 now shows how to enhance that spatial signal in practice. The top row compares standard MLP projection with a simple convolution, and the sharper heat maps on the right indicate that the convolution better preserves local structure. The middle tomato panels illustrate that adding the spatial normalization layer increases contrast between object and background patches. The bottom row then shows that combining both tweaks in iREPA yields diffusion features with much crisper, more localized similarity patterns. So, after Figure 6 showed the mechanism changes, Table 1 reports how those tweaks translate into numbers across training settings. The left block varies encoder size and shows that iREPA boosts inception score and lowers FID for all three perception encoders, with gains growing for larger encoders. The middle block scales diffusion transformer size and again shows bigger models benefiting more. The right block changes alignment depth and still shows consistent improvements, which signals that the method is quite robust. So after Table 1 summarized final metrics, Figure 7 tracks how those gains emerge during training. Each panel plots FID against training steps, with blue for standard representation alignment and red for the improved variant. The top row shows smaller SIT-B models, and the bottom row shows larger SIT-XL models across many different encoders. In every panel, the red curve drops faster and finishes lower, which means accentuating spatial features consistently speeds convergence and improves final image quality. Alright, Table 4 extends the story by adding classifier-free guidance into the mix. The left half, without guidance, shows that iREPA improves inception score, lowers FID and SFID, and slightly boosts precision and recall for every encoder, and at both 100,000 and 400,000 steps. The right half with guidance keeps the same pattern, and the absolute numbers get even stronger. This consistency suggests that emphasizing spatial structure helps regardless of guidance strategy or training duration. So the key message is that spatial structure in encoder features, not global classification strength, is what really powers better diffusion generation, and that a tiny change like iREPA can reliably harness that structure for faster, stronger training. This shifts how we should choose and design vision encoders for generative models. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.